is Angpo. Bhutan e-learning project welcomes you all to this lesson. I am Sushmika Tamang and this is a physics lesson for Key Stage 5, that is for classes 11 and 12. So today we are going to learn about fluid resistance, terminal velocity, surface tension, capillarity and their applications. Have you ever tried skydiving? Probably not. Now you're going to watch a video which will give you a virtual experience of skydiving. Please watch the video carefully and see what happens. So this is you just jumped off from the plane. So you have mass m. So as you jump off, you are pulled down because of the force of gravity, which is equal to mg, which is also called the weight of your body. So as you go down, there is this upward force, resistive force, which pushes you back because of the air. That is called air resistance, or also called drag force. So drag force is usually, I'll represent here by Fa. So there is this drag force acting on the body. So as you drop down, your velocity increases exponentially, okay? Your velocity will be increasing at rapid speed. At the same time, the drag force will also increase rapidly. You can take example of riding a bicycle. As you go slowly, your hair is blown off slowly. But if you increase the speed, your hair flies away. So that is the same thing. When there is an increase in the speed, there is increase in the opposite force. So this force, drag force, is directly proportional to the velocity. More the velocity, more the drag force. Now, let me remove the proportionality with equal to sign, and then you will have a constant which is called drag coefficient. So this drag coefficient also depends on few things. It depends on the atmosphere in which it is falling. It also depends on the surface area of the body. Okay, we'll talk about it later. Now, as I said, the velocity will keep on increasing, drag force will also keep on increasing, and one point you will reach when the two forces become equal, which means Fa becomes equal to Fg. At that time, the body reaches constant maximum velocity, which is called terminal velocity. So it will move with that velocity, which means there is no acceleration. So let's see what happens, or what is the value or expression for terminal velocity. So here at terminal velocity, Fa becomes equal to Fg. Now we'll just replace it. Fa is kV. So this time V is represented by Vt. It is equal to Fg, which is mg. So terminal velocity will be equal to mg over k. So this is the expression for terminal velocity. Now this has a huge importance. From here you can have different situations. For example, with the mass, how is terminal velocity related? Suppose you have, let's say, a metal ball and a plastic ball. Let's say their sizes are equal, but their masses are different, okay? So naturally metal ball would be heavier. So if these two balls are dropped from the same height at the same time, which one will reach the ground faster? Definitely it is the metal ball. Why? Because it has a greater mass and it is directly proportional to terminal velocity. So greater mass, greater speed, that is why it will reach on the ground faster than the plastic ball. Okay, here I talked about K, drag coefficient. This also has some impact on terminal velocity. For instance, suppose you take example of military parachute and commercial parachute. Usually the military parachutes are smaller in area and the commercial parachutes are bigger in area. Now if they are dropped from the same height, which one is going to reach down faster? Military has a small area, surface area, and then the commercial has a bigger one. So naturally military one will be dropping down fast because here K depends on the surface area. So terminal velocity is inversely proportional to K. So if the surface area is less, it will have a greater velocity. That is one reason why military parachutes are having smaller area. You don't want to be seen by your enemies falling down slowly, but commercial one is for sightseeing, so that is why it has a bigger area. Okay, so now suppose if there is no air. Right now we saw fluid resistance or air resistance on a body. Suppose if there is no air, it's vacuum, and you have the same two balls, metal ball and plastic ball. And if you drop down from the same height, what will happen? Which one will reach down faster this time? Both of them will reach down at the same time because there is no upward force. So that is what happens if there is no air. And this you can actually represent graphically.
Gravity and how it affects an object. We will look at an object falling in a vacuum with no air resistance and then how it affects an object falling through air.
Okay, now if you have to express velocity, how velocity changes with time in presence of air resistance, then what happens? As you saw, initially your velocity increases rapidly and after some time it becomes constant, maximum constant. So this is your terminal velocity. So this is how you represent change in velocity in case of air. So it shows that the velocity increases exponentially. Now if there is no air, if there is vacuum, then what happens? Your velocity will increase linearly with time because there is no upward resistive force. Okay, now this was the case when there was only air. What if the body is moving down in a liquid? If you drop a body in a liquid, this time you will have three forces acting on the body. One force, the same, downward force, pull of the earth. Another force is viscosity, because of the viscosity of the liquid, which would be upward. I'm sure you know what is viscosity. Viscosity is a resistive force between the layers of the liquid. So that will determine the flow of the liquid. So there is this viscous drag when a body flows in this liquid.
Viscosity quantitatively by measuring the rate at which a metal ball falls through a substance. The slower it falls, the more viscous the liquid.
Okay, so you see this is your body it's a spherical body having radius r, and there is downward force due to gravity, Fg, and upward force, which is drag force or force due to viscosity also we call it here, and then this is the upthrust. So now you can see there are three forces acting on the body, one downward, two upward. So three forces will be acting on the body, and now let's see this time what will be the terminal velocity. Now what happens as the body drops? When will it reach terminal velocity? When the upward force becomes equal to the downward force. So that time the body will be reaching maximum constant velocity. At this time you will have to put the values equation, and then finally you get the expression of terminal velocity, which is equal to 2r square g density of the body minus density of liquid divided by 9 eta, and here eta is coefficient of viscosity. So now it's a long process here. So after simplifying the equation, we get this formula for terminal velocity, which is slightly different from what we got initially because there are three forces acting on the body. So now here everything is clear. 2r represents the radius, g is the acceleration due to gravity, density of the body, density of the liquid, and then here eta is the viscosity, or also called coefficient of viscosity. Now from this we can have three different situations. First situation is if the density of the body is more. See, if the density of the body is more, your terminal velocity will be positive. Or more specifically, if the density of the body is more than the density of the liquid, the difference will be positive, which will make terminal velocity positive. So what does it mean? It means now the body will drop down in the liquid. Second situation is, what if the density of the liquid is more? If the density of the liquid is more, what will happen now? The difference will be negative, which will make the terminal velocity negative. So density of the body will be lesser, density of the liquid will be more, so the difference will be negative. So what does this mean? This means this time the body is going to move up, not down. Now where does this happen? Where do you see this situation? Here I have one perfect example. If I shake it, you can see the bubbles are going upward. So this means the body, which are the air bubbles, are lighter than the liquid, so that is why it is rising up. Okay. Now the last one, when the density of the body becomes equal to the density of the liquid, what happens? That time the difference is zero. So the terminal velocity becomes zero. It means what now? It means now the body is not going to move, it'll float. Okay, so these are the three cases of terminal velocity in a liquid. You can see pond behind me, and there you can see insects walking. You can see leaves here, and on the leaves you can see raindrops, spherical raindrops or spherical dewdrops. Now, have you ever wondered why all these are happening? Why are these natural phenomena there? It is because of one of the forces called cohesive force, which exists in liquid. So now what is cohesive force? Cohesive force is a strong attractive force between the molecules of same liquid, let's say. So here what happens, the molecules of liquid try to attract one another together. So when they attract one another together, especially on the surface of the liquid, they are pulled down and the surface becomes like a stretched membrane, and that will decrease the surface area, and since the surface has now become like a stretched membrane, it becomes easier for the insects to walk, and that is the reason why they can walk easily. We humans can't because we have more mass. Now about the spherical shape of the dewdrops. It is because of the cohesive force. Here the molecules inside will try to attract one another too close, making the surface area minimum. So sphere is the shape which is supposed to have smallest possible area, surface area to volume ratio. That is why the raindrops are usually spherical. But as you can see in the pictures, it is almost like this, not completely spherical, and that is because of the force due to gravity. The pull of the earth makes it a little elongated. That is why it's not completely spherical. Now we have understood what surface tension is. There are few factors which affect the surface tension of liquid, and for that we are going to I'll do one demonstration, and then what you will do is you will predict first what will happen, observe what will happen, then explain to yourself what is the reason for the observation. Okay? So here I have water in a container, and now I am going to sprinkle this chili flakes on this water surface. What will happen? Yes, it will float. Now in this I'm adding a drop of liquid soap. What will happen? Okay, let's see. See, the chili flakes are moving towards the corners of the container. What could be the reason? Let's see whether your explanation and my explanation matches or not. The reason is because soap is sparingly or less soluble in water. So when soap is added to water, it reduces the cohesive force. So which means now the molecules are not very much attracted, they are loosened. So that way they will be a little further apart, and that will increase the surface area and decrease the surface tension. For that reason, the flakes are moving towards the corners of the container. There are some other factors which affect the surface tension of the liquid, and one is temperature, and that you can check yourself at home taking the same materials. Try to heat the water and then see what happens to the chili flakes. So then you can relate yourself how temperature is related to surface tension, or how temperature affects the surface tension of the liquid. Okay, so that you try yourself at home and then give your result to your concerned teachers, or you can keep it to yourself. Learn more about surface tension from this demonstration. So here I have two capillary tube. One has a bigger diameter and this one has a very small diameter. Now I'm going to dip both of these capillary tube inside the liquid, and then you will tell me before, you will predict what will happen. Okay, to yourself you can predict, and then later you can explain to yourself for the observation, what could be the reason for the observation. I have a colored liquid here and I am dipping the two tubes in this liquid. What do you see? There is rise in the water level, and the water level rise is more in the smaller tube and less in the bigger tube. The rise of this water level is called capillarity. Okay, this process of rising of the water level or even dropping, this process is called capillarity. Now, what is the reason for the rise in the water level? The reason is again surface tension. As I said, there is this cohesive force. So when the tube is dipped in the liquid are attracted, the liquid molecules attracted to one another and they are rushed in. So there is cohesive force, which is again surface tension. But again, there is one more force acting here, that is adhesive force. Now what is adhesive force? Adhesive force this time is the force, again attractive force, but between two different substances. Here you have solid and liquid. So adhesive force is the force which will attract the solid molecule towards the liquid molecule. For that reason, the water molecules are attracted towards the glass, that is the solid. So that is one reason why there is rise in the water level. So the reason is, one is surface tension or cohesive force, and the other one is because of the adhesive force. So in the demonstration, you saw that there was rise in the water level or liquid level in the two capillary tubes, and the rise was higher in case of thinner or capillary which was smaller in diameter than the one which was a bigger diameter one. So here the rise was lesser compared to the first one. Now what could be the reason for this difference of rise in water level or liquid level? The reason is explained by this formula, which is called ascent formula. This is called SN formula, and this formula helps you to find the rise in the water level of the liquid in the capillary tube. So here S represents the surface tension, theta here represents the angle of contact. Now what is angle of contact? I'll explain here. So this is the meniscus of the liquid level. So it is touching the water, the solid surface here and here. So these are at point of contact. So from the point of contact, you have to draw tangent on both solid and liquid surface. So to the liquid surface, as you know, this is the liquid surface, liquid meniscus, you draw a tangent inside the liquid. And on the solid surface, from the point of contact, you draw another tangent. So the angle between these two tangents is called angle of contact. So angle of contact, a given pair of solid and liquid, is always the same. So for this glass and liquid, the angle of contact is theta. Okay, and A is the radius of the capillary tube. Here I have written as R, small r and capital R, just to show that one small r is smaller and capital R is bigger. But in the formula, A here is the radius. Generally A represents the radius of the tube. D is the density of the liquid and G is the acceleration due to gravity. So now here, height is inversely proportional to the radius of the capillary tube. So more the radius, lesser the height. Lesser the radius, more the height. Now since the radius of thinner capillary tube is small, so there will be more rise in the water level in thinner capillary tube. So that is the reason. You see the application of capillarity every day in your life, starting from the morning. What do you do in the morning? You wash your face, right? And then after that, you take a towel to wipe the water off. To dry the water off, you use the towel. Why? Or how does towel absorb this water? Towel has small capillaries, which are called pores. So these pores, when it is kept on the face, it will absorb the water. So that is how capillarity is applied. And you know there are some towels which do not absorb water perfectly as the others, the more expensive ones probably. So that is because the capillary in the less absorbing towel are bigger. Okay, again, after you wash your face, what do? You pray. So when you pray, you light a butter lamp. Butter lamp has this wick, cotton. The cotton will also absorb the butter or the oil from the thing because of capillarity. Okay, the rise is there because of capillarity. So these are few applications which we know, but we are not very mindful to link it with physics lesson. So I would like you all to see further applications of all these surface tension, capillarities in your day-to-day life, and then you may note in your notebook. And to start with, I have few areas for you all to explore. I have few questions. In terms of questions, I have suppose you are a soldier. You have jumped off a helicopter, then you are falling down. What happens? Your velocity increases and you reach a terminal velocity. At that time, if you open your parachute, what will happen? Okay, so that is your first area to explore. Second one, when you go to a hotel, you ask for a soup. If the soup is cold, you don't like it, right? You like hot soup. So why do hot soup taste better than the cold one? And finally, you see in the villages, farmers plow their field. So do you think plowing the field is going to retain the moisture in the soil? So these are the areas you can explore further and take help from your concerned teachers. So with this, we have come to the end of our lesson. I hope you enjoyed my lesson. Thank you for attending this class and see you all in my next class. Thank you.